Hello my friends, and welcome to the final practical activity of this part 9 dimensionality reduction. We already built two dimensionality reduction models. First, principal component analysis, and then second, linear discriminant analysis. We got amazing results with both, but slightly better results and actually perfect results with linear discriminant analysis. So now we're hoping that with our third tool of the dimensionality reduction toolkit that we get at least the same thing as PCA or that same perfect result as with LDA. And you might guess that since now we're about to add a kernel, and as we saw with SVM and kernel SVM, adding a kernel always improves the result. Well, you might guess that we're about to get amazing results as well. Alright, so let's build that final model. But before this, let's make sure everyone here is on the same page. I give you the link to this whole folder right before this tutorial, so make sure to connect to it. And now here we go, let's enter part 9 and then section 45, Kernel PCA. And as usual, we're going to start with Python, and this Python folder contains two files. First, the Kernel PCA implementation in the IPYNB format, and of course the same dataset, wine CSV, which is a dataset of many wines, many different wines. Each row corresponds to a wine, and for each of these wines we have these features from the alcohol level to the pro line. And then for each of these wines we also have the customer segment, which is the segment of customers to which the wine belongs to, in the sense that all the customers of each segment, and we have 3 segments in total, have the same preference for such wines, okay? And so now the challenge is to build a logistic regression model combined to some dimensionality reduction techniques applied to this dataset so that we can end up with a less complex dataset, which at the same time will provide an excellent way for the logistic regression model to learn the correlations between all these features and the dependent variable. Alright, and then for each new wine we will deploy this predictive model to predict the customer segment to which this wine belongs, so that the owner of the wine shop can recommend each new wine to the right customer. Alright, so that's the exact same case study as before, and now let's open this implementation with either Google Collaboratory or Jupyter Notebook. As you can see, I kept this PCA implementation and this LDA implementation so that we can compare. And now, well, as usual, this implementation is in read-only mode because you all have access to it. So let's create a copy by clicking File here, then save a copy in Drive, because indeed in this copy we will re-implement the cell that implements Kernel PCA. Let's get rid of this so that we can have clearly the 3 dimensionality reduction techniques. And now there we go, let's implement Kernel PCA. But first, this time let's upload the dataset first so that we can, get the assistance of Google Colab. Right now our notebook is connecting to runtime, there we go. Then let's click upload. We'll end up in the linear discriminant analysis folder. So let's just do the whole path again. So this is the whole machine learning A to Z folder. Let's go inside and let's go to part 9 dimensionality reduction and section 45 Kernel PCA, Python and wine.csv. Open, okay, and there we go. Now our notebook is connected. Okay, so now we're gonna do 2 things. First, we're gonna remove that cell, put it in the bin so that we can re-implement it, but also let's, remove all the outputs by trying not to look at them, I hope you didn't look at the results, but anyway, I'm sure you expect an amazing result as well. So let's just remove the output here. That's the visualization of the training set results, and this one, the visualization of the test set results. All right, then let's take the table of contents, applying Kernel PCA, and there we go. We are ready to implement this. So let's create a new code cell. And now, do we want to re-implement this, from the very scratch, or do we want to be efficient? And well, of course, that's really my spirit as a coder, as a machine learning programmer. I always want to be efficient. And by that, I mean that, the Kernel PCA implementation is super close to the PCA implementation, because basically it will be almost the same, except that we will have to add a kernel in one of the inputs. So what we're going to do, in that spirit of efficiency, is we will go to our PCA implementation. We will take that cell, because you're going to see that it's going to be almost the same. So let's paste that here. And now, the only thing that we have to change is first the name of the class, but not the module, because the class we're about to import to implement Kernel PCA still belongs to this decomposition module by the Scikit-learn library, and that class is of course Kernel PCA, just like that. So that's the class. Then, well, let's give a different name to the object. We're not going to call it PCA, but we can call it, KPCA, as you want, Then of course here, when we call the class to create an instance of this object, which will be this KPCA variable, well, of course we need to call the right class, which is Kernel PCA. And now inside this class, well, same, we have to choose a number of extracted features, which is still given by this argument and components. But since now we're working with a kernel, we're doing Kernel PCA, well, exactly the same as when we transition from SVM to kernel SVM, well, we simply need to add a kernel argument here. And we'll actually choose the same kernel as with kernel SVM, meaning the RBF kernel, which is the radial basis function kernel. So there we go. That's our second argument here. Kernel equals, in quotes, well, RBF, radial basis function. And now let's see what there is left to change. So this line is good. The next line of code, well, same. In order to perform the Kernel PCA dimensionality reduction technique, well, we only need the features of xtrain and not the dependent variable ytrain. So all good, that's the same as PCA, but not the same as LDA, which required the dependent variable ytrain. So all good here. However, be careful, we renamed our object not PCA, but KPCA. So same here, KPCA. And now, my friends, this implementation is over. That's what happens, when we're being efficient. The implementation is sometimes completed faster than expected. And that's because, as you can see, Kernel PCA is very similar to PCA, in terms of its implementation. Okay, so now we're just ready to do a run all again. We have our data set. Our implementation is all good. So let's do this. Let's click runtime here and then 3, 2, 1, run all, go. All right, so now all the cells are running, our logistic regression model is built, and as expected, well, we get, of course, an accuracy of 100%. I've rarely seen some cases where, the non-kernel version of the model beats the kernel version of the model. It can happen, but it's very rare. So there you go. Here, of course, Kernel PCA manages to beat the PCA model. Thanks to that kernel, well, we fixed that incorrect prediction which we had, remember, in PCA right here. So all good here, we get a 100% accuracy. And now let's have a look at the results. How Kernel PCA was able to separate our classes in the test set, right, which are new observations on which the model wasn't trained. Well, there you go. That's our two principal components, PC1 and PC2. And now in a new dimension, once again, because the Wines observation points here are arranged in a different way than with PCA, right? We have very different arrangement of the points here. We can see them more dispersed than here, right, with our PCA. Well, that's because we are in a new dimension. We are with different dimensions, PC1 and PC2, meaning different extracted features. So that's totally normal that our observation points, the Wines here, are arranged in a very different way. That's because we are in a different dimension in which, well, the logistic regression model was perfectly able to classify our observation points with these 3 prediction regions. And same for the LDA, the observation points are arranged differently because, once again, these are some different dimensions. We are in another dimension here thanks to these extracted features. So you see, this dimensionality reduction technique is pretty fascinating because it basically allows to create a new space of dimensions. And in some new dimension, well, indeed, we can perfectly classify some observations, like it is the case for linear discriminant analysis and Kernel PCA. Now, what I recommend for you to do is to practice this on other datasets. So I recommend, for example, to check out the UCI-ML repository platform and go to the classification section and try the Kernel PCA on other datasets. And you'll see you will end up with similar results with some prediction boundaries like that, separating well the classes. Please share your results in a Q&A, especially the ones where we clearly see an improvement with Kernel PCA with respect to PCA. Maybe you'll find some datasets where PCA performs poorly, but then by adding a kernel with Kernel PCA, you will get much better results. So please share this. I'm actually very interested to see what you get. All right, thanks in advance. And now congratulations, this new chapter on dimensionality reduction is done. And now we're going to move on to the final chapter of the course, part 10, model selection and boosting, where you will learn your 3 last and very important tools, which are first, k-fold cross-validation to evaluate your machine learning models the best way, then parameter tuning to find the best values of your hyperparameters, and finally, the cherry on the cake of this course, I will teach you and give you the XGBoost model, which is one of the best and most powerful machine learning models for regression or classification. That will complete your master machine learning toolkit the best way, and until then, enjoy machine learning.